Thank you, Demir, to all the organizers for the meeting and for the invitation. Given that the people who might not have known have now been through this long tutorial, I guess I can assume everyone knows what reverse mathematics is. I think the only thing you need to remember about it for this talk is that it's a method of measuring complexity of mathematical theorems based on systems in which they're second order arithmetic in which they're provable. And that there's a commonly accepted base theory called RCA naught. What it is almost irrelevant. And the other thing you should know is that the subject started off with almost all theorems of mathematics turning out to be equivalent to one of a small number of systems of logical axioms that were called the Big Five. No one seems willing to accept responsibility for that name, but it's stuck somehow. And then after a couple of decades, things started changing. And instead of just being a small number of systems, there turned out to be a huge array of different mathematical theorems that were proof theoretically different from each other and formed a very complicated structure, which became known as the zoo of reverse mathematics. Maybe you've seen a picture, but the mirror is responsible for many of those pictures. And there's a computer, they're so complicated, there's a computer program now for producing the pictures. But it was that situation that led to this talk, in the sense that I was a couple of months ago preparing what was going to be a public lecture on reverse mathematics at Berkeley last month. And I had sort of reached the point explaining all the things I just said at great length, or some length. And I came to the zoo and I put up this picture that filled the whole screen and was totally illegible. And when I came to that in my preparation of my talk, I said to myself, well, this is like a situation I've seen before. And the situation was with the Turing degrees, where for years, people conjectured that they were simple in some nice way and that they were homogeneous, they were decidable, whatever, all kinds of different conjectures. And then as time went on, it became more and more complicated. And the structure became very complicated. And every new theorem put in the criteria for having a good new theorem was it was some new construction or it produced some new situation. And so it became very complicated with no organizing principles. And what happened at that time was that there was a shift in viewpoint or emphasis, or at least people started looking at what we might call the global structure of the Turing degrees. Questions about definability, automorphisms, what can you say globally about the structure? And there was a lot of results. And the results were all in the direction that it was very complicated. I'll mention a number of them as we go along. But I thought to myself, why don't we do the same thing with reverse mathematics? We should view it as a degree theory. After all, it's an ordering relation on the strength of different theories. So it looks just like something like the Turing degrees in the sense that, oh, this is harder than that. You have a partial ordering, you could have equivalence constants, you could do the same analysis. And I said, well, why don't I think about that for a little bit? And much to my surprise, it turned out to be quite easy, well, at least elementary, to analyze this structure and prove a whole array of theorems. Oh, this was working just a few minutes ago.
That's not
Now, okay, that is not. Pointing at the wrong part of the screen. Okay, so this is what I just said, but the wasn't. And so I wanted to do the same thing with reverse mathematics. So what should the setup be? What are the basic objects? What corresponds to sets for the Turing degrees? Well, they're theories, which are just sets of sentences in second order arithmetic. And if we're thinking reverse mathematics, so every theory should contain the base theory, RCA naught. So those are the objects, and we order them by strength of provability, that T is stronger than S if T proves every sentence in S. And then what do? If you're a recursion theorist, a compute degree theorist, you mod out by the equivalence relation of things being equivalent. Those are the things that reverse mathematics studies as well, and those are the degrees. And you're going to say that you're going to inherit the ordering from the theories to the degrees, and you check that yes, it's well defined. And then, as I said, you try to prove theorems, and it turns out that you can prove a whole array of what look like deep theorems by very elementary methods. I mean, they look deep if you're thinking like the Turing degrees, but basically everything that I'll mention, all the theorems I'll mention in this proof, you can prove just using the methods that you learn in a first order logic course. Well, maybe with some little trickery here and there. Things like the deduction theorem, compactness, completeness, Gödel incompleteness theorems, back and forth arguments, quantifier elimination, sort of the bread and butter of a first year logic course. Now you might think, oh, I'm going to use the Gödel incompleteness theorem in second order arithmetic, and do I need to check what every time someone uses the incompleteness theorem for another system, they say, oh, well, you can just check that everything works. You can develop whatever you need. So in this case, we don't have to do that. There's a theorem in reverse mathematics about conservation that says that RCA naught is conservative for certain sentences that is over a first order theory. So conservative means that it doesn't prove any new theorems. So that means that if you're worried about what's provable in RCA naught, and it's a simple theorem like the Gödel incompleteness examples, then it works the same way for RCA naught that it does for sigma 01 PA, which is a weakening of piano arithmetic in which Gödel worked, but which is now all the proof theory books use it. So you don't have to say it all the 50 pages of details work out. You just can cite this theorem. So after I started thinking about it, I thought maybe I should check that all this was known. And so I asked a few proof theorists who said, no, they never heard of anyone doing this. I said, great, so I'll keep working. They mentioned a couple of similar things, like instead of ordering by provability, you can order by relative interpretability. That means what you might think it is, you can define this, but you want to work for theories in different languages. So you can't talk about one theory proving the sentences in another language. So you have a way of interpreting the structures or the sentences and transferring between the two subjects. And anyway, that was a subject that was started by Tarski, and was studied quite in depth. So they talked about the degree. There were papers, books about the degree theory in this notion of degree. And it was mainly designed to study relative consistency instead of provability strength. And it turns out, though, that it is a study of provability strength, it only looks at the pi01 sentences. That is, this notion is equivalent for the arithmetic situation for one theory proving all the pi01 sentences. And then I knew about people who had worked on the pi02 sentences, because the first one who did it with Ming-Jung Kai was a student of mine, thought about this. And he and various other people, mostly at Madison, have proven various theorems about the structure. Again, things like minimal pairs, joining, the same kind of theorems that Lindstrom proved about the interpretability degrees that were common for the Turing degrees. But they weren't arbitrary sets of things. So not reverse mathematics. So what I'm about to present is really work in progress. In fact, some of the results were only proven this week, and others I thought this morning I think I might be able to prove. We'll see. So on the other hand, what I discovered when I was looking into the history, actually I was looking up algebraic facts that I needed about strange lattices, or what you might think of as strange lattices. And I discovered that Tarski had actually introduced this notion in a much more general context back in the 30s. So there are several papers in the late 20s and early 30s in Polish and German, which sort of look at this notion of strength, relative provability strength, and analyze the algebraic structure. And this led Tarski to his work on Boolean algebras in a way. And by noticing that he could translate back and forth between provability and Boolean algebras. So he proved quite a number. I now know that he proved quite a number of the theorems that I proved, but only 100 years ago. So that was very interesting. He had another. The reason I couldn't find this directly was he had a name for it that no one ever used again. He called it the calculus of systems instead of degree. Well, no, there was no degree theory of any sort then, so he invented a name. And I found out about this about papers written about Tarski in English more recently, and there were several of them. And so, and I've now managed to get hold of English translations of some of his papers, and I know something more about what he did, but I'm sure he's proven more than I know about it. But the striking point for my, when I was looking at it was how different the situation in reverse mathematics was from the situation in Turing degrees and all the other degree theories that usability theorists ever studied. So let's head on to the results. So DP is the structure of the equivalence classes of theories under equal provability, degrees of provability. And as in the Turing degrees, there are natural subclasses, so the RE degrees, the degrees below the jump, the halting problem, the arithmetic degrees. So it seemed to me that the natural structures, substructures in terms of provability were the finitely axiomatizable theories. I mean, that's a very prominent class and has a lot of interesting proof theoretic and algebraic properties. And then the axiomatizable theories, what we call it. That is, there's a recursive or equivalently or recursively enumerable list of axioms. So those I want to single out as the interesting substructures. So this is a note responding to a question from, I gave this, I should apologize for the people who were at this talk I gave on Zoom, or the talk I gave last month. Much of this is the same. But this is different because it answers a question raised in the talk, raised after the talk. And that, so I'm at various points, finite axiomatizability is going to be very important. So someone asked about recursive RCA naught. And I said, oh yes, it's finitely axiomatizable in second order arithmetic, which is not hard to see once you develop enough of the Turing machine property machinery, but it plays no role in what happens next. But it seems to be bothering people. So I'm going to go on contrasting the situation that's here with the one that developed in the Turing degrees over the past I don't know, a long time, many decades. And I'm going to omit all the references because that would fill up the lecture. So the Turing degrees basically is a partial ordering, but it's an upper semi-lattice. It has zero with size continuum. It has a countable predecessor property. The RE degree is countable, also an upper semi-lattice with the same zero. Neither is a lattice, neither is distributive. All the nice lattice theoretic properties fail, basically, that you think about it. So, how do we start with DP? Well, we first check, is it an upper semi-lattice, is it a lattice? And it's easy enough to define the operations on theories and then check that they're well defined. So you have a theory. So look at its closure under deduction. And that I call S bar. Now define imps and soups. Well, you define operations and then show that they're imps and soups. So inf is simple. If you have two theories that are both closed under deduction, then their intersection is closed under deduction. And it's easily seen to be the inf in the provability relation. If you want to take the join, you can take the union, but then you have to close, because the set theoretic union is not closed under deduction in general. So, but that's the obvious natural move, and that gives you a soup and an inf. And there's a 0 and a 1. The 0 is RCA naught, and 1 is a contradiction. That's bigger than every theory. Every consistent theory is provable from a contradiction. So now this closure operation produces what I call a canonical representative of the degree. Namely, you take any element of the degree and take its closure under deduction, and that's in the degree, and it's the biggest one under set theoretic containment. Anyway, it's a nice representative, and I'll frequently, as degree theorists do, confuse notation between the degree and a representative, a nice representative, because too many fonts otherwise. So that's what DP is, and the axiomatizable and the finitely axiomatizable are both distributive lattices with 0 and 1 as well. Okay, so now not only are they distributive lattices, but if you look at the full structure, DP, it's complete. And what's the proof? Well, you have a bunch of theories, take their union, close under that's a theory. It might be inconsistent, but that's fine. That's the inconsistent theory. And that is going to be a soup. And if you take the intersection of the closed versions. Now, why is it distributed? Okay, so this is an exercise in unraveling the definitions of predicate logic. So here's an example. In order, you have to prove distributive laws hold. This is a good one. And what you do is you figure out what it means to be the imp of two theories or the soup of two theories. And then you do manipulations by taking conjunctions and disjunctions of formulas, and lo and behold, it's distributive. So there's a proof in case you want to look at it. You want a time. Completeness is what I just said, is that you can take the set theoretic things and either just intersect or join and close. So an important point here, though, is this will get a name eventually later, but if you look at an infimum, it only depends on a countable subset. This is how big is this structure? Well, it's size continuum, because any set of sentences is a set of sentences. And then the equivalence relation is not too bad. But if you look, so an arbitrary join might be a join of uncountably many elements, but that doesn't matter. Why not? Well, it's the compactness theorem. In order to get anything, how many things could you use? You're only countably many sentences, each one of which could only have used finitely many axioms. So you only needed countably many of them. So joins are really just countable. This is all elementary logic, let's say. Now, what happens inside the axiomatizable theories? Well, when there's a join, it's still a join. If it happens to be axiomatizable, it's still it happens to be. If it isn't, it isn't, then it's not there. So it's not a complete lattice. It's, after all, it's countable. There are a lot of infinite subsets. But it inherits what it can. Now, what's the structure of these natural subtheories, substructures? So the finitely axiomatizable theories, what are they? Well, I claim that they're an atomist Boolean algebra. Well, you know this algebra. This is what I thought was a Lindenbaum algebra. Is that if you look at any theory and you look at the formulas of the theory under provability, that forms the equivalence classes form a Boolean algebra. What do you think? What's the complementation? Negation. And then you have a and and or. So it's not a surprise now, but it was a surprise 100 years ago. And in fact, when I looked into the history, even though I always thought it was a Lindenbaum algebra, it was really Tarski who discovered it. And if you look at Wikipedia, it's called the Lindenbaum-Tarski algebra. But and so now, so that shows it's a Boolean algebra. What about its being atomless? Well, that's the incompleteness theorem. Why is that? Well, the incompleteness theorem says that if you have even an axiomatizable theory, then there's an arithmetic strong enough to do whatever, then there's an undecidable sentence. Well, that means there's a bigger theory. You add on one, you can add on the sentence or its negation, and you have a bigger theory. Well, that means that it's upward dense, but it's a Boolean algebra, so if it's upward dense, it's downward dense by algebra. So that's the incompleteness theorem. So then I started thinking about, could I say more about the issue of density? So we have upward density in the finite. So the finite part is the finitely axiomatizable things are dense. What about the whole structure? What can we say about density there? So again, influenced by my experience in the Turing degrees, I said, if you want to look at density, the thing to do is to look at the simplest counterexample to density. That is, you have two elements with nothing in between. Now that's called that one is a minimal cover of the other. So I said, what can we say about those? So that's what we're going to look at, that question. What can you say about minimal covers? So let's let the situation remember the situation of Turing degrees. So every degree in the Turing degrees has continuum many minimal covers, but some degrees are not minimal covers. Every degree from some point on is a minimal cover. In the RE degrees, they're dense, so nobody. So that's the Turing degrees. What happens in provability with reverse mathematics? So it turns out the 0 degree is not a minimal cover. But everything else is a minimal cover. And in fact, if you take any theory S and any formula in it that's not an RCA, provable in RCA not, then you can find an R below S such that S is a minimal cover of R, and the only thing that separates them is this one formula we picked at the beginning. So not only is it minimal over something, it's minimal over lots of different things, because you could pick different formulas to leave out and check that you actually get differences. Okay, so now, what about particular ones? Well, let's look at one, the contradiction. it's a degree, it's a minimal, I claimed it was a minimal cover. What's it minimal over? Well, it's a theory such that you can't get anything bigger. So that means there's no formula gamma that you could add on without making it a contradiction. What do we call those theories? Those are the complete theories. That they decide every sentence or its negation. Tell you they decide every sentence. So one is a minimal cover of exactly the complete consistent extensions of RCA9. And that means they're definable. Being a minimal cover is definable. These are called minimal. When your one is minimal over you, you're called a coatom. So this says that the proof theoretic notion of a complete theory is definable in the lattice of provability degrees. They're just the coatoms. And not only that, you can, if you're a complete theory, what could I said you were a minimal cover of something, but you can say exactly what you're a minimal cover over. So you can just take two different complete theories, look at their intersection, and each of them will be minimal over that intersection. This is all chasing the algebra and the predicate logic kind of things. So nothing much is going, I mean, there's a lot coming out, but there's not. Now, if you look at the finitely axiomatizable theories, none of them has a minimal cover. This is again a Gödel type. Okay, so that was one analysis. You get a lot of information about where density fails. Next algebraic fact that look at was complements. You start off with a Boolean algebra at the bottom, the finite axiomatizable one, so they have complements. What about the other theories? Can you find complements for other theories? In the distributive lattice, we know what it means to be a complement. So what happens in the Turing degrees? Well, you don't even have a 1, so the note complement doesn't mean anything. So that, forget about the Turing degrees here. So this is what everyone knows that a complement is. And it's unique. An element of an algebra lattice has a complement that has only 1. So what are the complemented elements in the degrees of provability? Turns out they're exactly the finitely axiomatizable ones. And this argument essentially boils down to compactness. You have to play around. If you have a complement, so these two join up to a contradiction, so there's a finite piece that makes it contradictory, and then you play around with the algebra and see that you can get something that imps down and it goes both ways. So what does that mean? That means that the degrees of the finitely axiomatizable theories are definable in this structure. So this they're the complemented elements. Okay, so now I want to move into more esoteric lattice theoretic properties. So I should thank Marcia for this, because I learned about was that a question? No. Okay. I learned about these sort of lattice theoretic notions as a result of some work that I did with Marcia Grozek on the initial segments of degrees of constructibility. It may seem very far away from this subject, but turned out to be very close. And we proved some theorem that needed the lattice that we were trying to embed to have certain properties. And they just looked like a strange list of properties to me. And I asked a lattice theorist, and he said, "Oh, those are the algebraic lattices." I said, "Oh, good, people know about this." And I couldn't even find out what they were. So I did long ago, when I remembered when I came here to this question. And so here are a bunch of the examples. of the definitions. So, so the first notion, not first on this list, for an algebraic lattice is what it means for an element to be compact. So an element X in a lattice is compact means that if it's below some join, then it's below the join of a finite subset. What kind, does that sound like compactness? Yes, that is compactness. And an lattice is algebraic if every element is a join of the compact things below it. Well, at this point, we know that the compact thing, well, it's obvious that the finite the axiomatizable series are compact by the compactness theorem. And and every element is a join. We already know every theory is a join of the senses that are true in it. So this is an algebraic lattice. Now, it turns out it has more properties. So one is being what I thought of was being pseudo-complemented, which is, this is not a complemented lattice. We already know that the non-finite axiomatizable things don't have complements, but they have things that are almost complements. They're half of being a complement. The biggest thing, if you want to take a complement of, let's say, A, so A, you want things, a complement is the biggest thing such that X, such the A star is the biggest thing such that for any X, it's the biggest thing which imps it to 0. It's also the smallest thing which soups it to 1, but this is half of being a complement. So these are called pseudo-complements. And so a proof shows that this is an algebraic lattice which is pseudo-complemented. So when I gave this talk, Dana Scott pointed out that, oh, it's also a hiding algebra. And I said, oh, I hadn't thought about hiding algebras. And then someone explained to me that hiding algebras meant what's called relatively pseudo-complemented, which is the same thing as complemented only inside every interval. And so the proof works. You get the same results. So this is actually a hiding algebra. So I knew what a hiding algebra was, but I don't think about it much. For those who don't know what a hiding algebra, this is a definition. But a better way of thinking of it is that it's a model for intuitionistic logic, because the pseudo-complement is the implication that you want for intuitionistic logic. And so this says that the structure reflects intuitionistic logic in a certain interesting way. Okay, and that's a definition of the pseudo-complement in terms of closure and joining. And the ordering. Again, you check that it works. Okay, so now we want to move into the what I call other aspects of the global. These are the algebraic aspects. You might think of these as local properties. A complement is this element as that element, the order. But the global questions are like the decidability of this ordering, definability, automorphism. Questions like that. So the situation with the Turing degrees, as we said, is very complicated. So how complicated is the first order theory of the Turing degrees? Well, it's as bad as it could possibly be. It's full second order arithmetic, true second order arithmetic. It doesn't have small generating sets. It has an automorphism basis consisting of 1 degree. That's a remarkable result. Blame it and wouldn't. It has at most countably many automorphisms. We don't know if there are any automorphisms at all, other than the identity. There are various things that are definable. Certain natural degrees like the Turing degree, the Turing jump operator, and all sufficiently large degrees that could be definable in second order, that are definable in second order arithmetic, are definable in the Turing degree. Homogeneity is another global property. This means that is it similar if you look in different parts, and more particularly, if you take some degree S and you look at the degrees above S, are they the same as the Turing degrees, or whatever the degree structure is? And this was a long conjectured property of the Turing degrees, which turned out to be a nice property. It was the same no matter where you started. That turned out to be false. And in fact, almost no two cones are isomorphic. On the other hand, we don't know that there are two different cones. So there's a fair amount of work to be done still on the Turing degrees. The recursively enumerable degrees are again complicated as possible. Their theory is true first order arithmetic. There are some classes of degrees that are definable, but there's not known if any single degree is definable or not. What happens with the provability degrees with reverse mathematics? Exactly, well, I'd say exactly the opposite of things that have so many different aspects, but certainly in the respect to the theory is exactly the opposite. The first order theory of both the finitely axiomatizable and all the theories as a whole are decidable. So this says that any sentence about anything that you've asked yourself about what's true about the what are there certain theories that have this property that they join up to each other, they inf down in other ways, they're ordered in strange ways. Any question like that you wanted to know if there was such a collection of theories, there's an algorithm that will answer that for you. So all the things that the zoo exhibit, all the structure that the zoo exhibits, you could discover that all those things existed just by applying this algorithm. This is not. That's the decidability for the degree structure as a whole. For the finitely axiomatizable theories, this is an old theorem. Tarski proved this. It's hard to know when Tarski proved various things. The results appear later and they say they're attributed to him. Some of these things that I looked up, Bart's thesis as a footnote, saying that Tarski had proved this theorem. And in another paper, I said, if you look in Bart's notebooks from his courses with Tarski, you will find the following proof. I have not yet found those notebooks, but I did find his thesis. But so this is Tarski. So he proved it, and he did this by a classical quantifier elimination, which tells you a lot about definability of the structure. But that's just for the finitely axiomatizable thing. The structure as a whole is much more complicated. I mean, it looks much more complicated, but it has all these continuum many elements. And here, what you want to realize is that, well, the finitely axiomatizable ones are the atomless Boolean algebra, and all the others are their joins. And those are the ideals in the algebra, exactly the ideals. And so this is really the question about the theory of the atomless Boolean algebra together with all its ideals. A two-sorted theory, a second order theory. And it turns out that Rabin proved that this theory was decidable. 60? And the proof is this is a very deep, hard theorem. This was a very celebrated result of Rabin's. He proved that if you look at the theory of two successor relations and the monadic theory of that you allow quantification over subsets, then that's a decidable theory. And he proved it by an analysis of automata on infinite binary trees. And doing an analysis in terms of automata theory. So this is a well-known and important theorem in computability in the sense of computer sciences, right? And he pointed out in his paper that the Adams Boolean algebra was its ideals was an example could be interpreted into the binary tree with two and an automata on it. So that's a theorem of Radham's. So what is that? So that tells us that all these questions about recursive mathematics, if you're just interested in does there exist an example of this, or for every degree, is there another degree having this property? You could do it by applying his algorithm. That algorithm turns out to be quite complicated. I'm not sure what the current status is in terms of the proof complexity, but it's I don't remember how many exponentials it was last. I haven't looked recently, but there have been several theses in proof in computer science trying to improve it. Other, if I remember correctly, or other results of Tarski along the same way. So now we want to talk about automorphisms of the whole structure. So we know that the structure is generated by the finitely axiomatizable ones. So if every automorphism of the whole structure of reverse mathematics is generated by an automorphism of the finitely axiomatizable theories, which is the Adams Boolean algebra. So we know how to build automorphisms of the Adams Boolean algebra. This is the classical back and forth argument going back to Cantor. And this was also proven by Tarski, according to the footnote in Vaught's thesis, that you could prove that the Adams Boolean algebra that theory is Aleph not categorical. Any two models are isomorphic, which gives another proof of decidability, but it gives a lot more because it tells you how to build automorphisms of the Adams Boolean algebra. I don't know how many people see this. I'm sure everybody's seen back and forth arguments. So everybody's probably seen that dense linear orderings have that property. And that's how you prove that without endpoints, they're categorical, decidable. So this is proof is like that, only algebraically more difficult. Because you don't have just ordering, you have to worry about preserving joins and ints and complements. So there are like several pages of algebra to tell you when you can do that. But it's that kind of proof. And if you sort of play with the argument, then you can build more than just one automorphism with certain properties. You can build ones with special properties. And that's what's coming up next. So, for example, you can prove that there are exactly continuum many automorphisms. It's a countable set at the bottom, so it can't have more than continuum many, but you can actually build continuum many automorphisms. And you can prove that if you take two finitely axiomatizable theories, there's not 0 or 1, of course, you can't move them. But if you take two non-trivial axiomatizable theories, there's an automorphism of the axiomatizable theories which takes one to the other. That's basically no change from the original proof. But that means, now you can prove there are a couple of other facts. If you look at two complete theories, then there's also an automorphism which takes one to the other. That requires a little proof. But the fact that you can move any finitely axiomatizable theory to any other one means that no particular degree is definable. Because look, if the two different degrees, they differ on some formula, two different theories differ on some formula. And so you can take one, you can switch them. You can take the formula in which this is phi and this is not phi. You could have an automorphism which interchanges phi and not phi, and that can't take that is an automorphism, so it moved one to the other. So you can't couldn't have defined one of them. Those automorphism preserves definability. Okay, so now if you do a little extra work, you can figure out exactly what the countable definable sets are in the structure. There are 8 of them. And we know them all already. So there are the trivial ones, oh, just 0, just 1, just 0 and 1. And then there are the finitely axiomatizable theories. And then you can take out 0, you could take out 1. You could take out both. So that's a list of the things we know are definable, and they're the only ones. And this is sort of a more, there's probably an algebraic proof, but my proof looks more like one by a recursion theorist. So first you do a little algebraic preparation. You have a countable subset that's not one of these 8. And you want to construct an automorphism which moves one of them to some that doesn't fix the set. So you want to move something to something not in the set. So you figure out, oh well, might as well assume it has 0 or 1 and 1 in it because you can modify it without changing definability. You can check that it can't split. If it splits the finitely axiomatizable ones, we already know you could switch them. So now we can assume that it doesn't split the finitely axiomatizable ones. So it either contains them all or it doesn't contain any except 0 and 1. And now you want to say, okay, now I've got a countable list of S's, SMs, and I want to not hit them, any of them. So you go along one at a time, and you say, aha, you build an automorphism, think I'm trying to extend by 1 element, and I'm worried about the ones in my given S that I want not to, its image not to be in this countable list. And you say, well, I want to define my automorphism on the next element of my given S and make sure that I kill one of the SMs. So you figure out how to do that. And you argue that you can't always do it. If you haven't eliminated it by various reasons, like something's too big, something's too small, then you can actually find something that isn't there. And that's based on the fact that you can throw away all the things that are finitely axiomatizable. And that's the outline of the proof. Here's the proof. Well, a longer outline. We don't need it. Okay, so that's an exact classification of the definable countable subsets. We've already seen that there are uncountable definable sets, namely the complete theories. So there are going to be, and there are lots of them, lots of undefinable, uncountable sets. And I don't see any hope at the moment of characterizing them. I mean, well, there's maybe one hope, but let me say a few words about the homogeneity issue, which is connected to the definability issue. So we want to look at cones. We're given a theory S, and which isn't 1. Cone above 1 is not interesting. So I had some thought about this, which I told Leo Harrington about, and the next day he sent me an email saying, I'm worried about that. So when Leo says he doesn't understand something, you should go back and look for the mistake. So I found I had 3 pages of algebraic computations, and I convinced myself of some false fact, which I fortunately discovered. So he told me this 2 days before I was giving the talk, so I found the mistake and corrected it. I mean, it proved the right theorem. So look at an arbitrary theory S. What those are the theories that are stronger than it looked like as a lattice. I mean, it's all the things bigger than S in the lattice, so it's a lattice, a distributive lattice. It inherits. So it really looks like a countable Boolean algebra with its ideals. And this is a theorem about Boolean algebras. So the atoms Boolean algebra, I don't know, maybe everyone, well, degree theorists know that you can embed every Boolean algebra into it. In fact, every partial ordering over semi-lattice, whatever, is a common. But it's also universal for the other direction, as you can map it homomorphically onto any countable Boolean algebra. And then the kernel of that mapping is an ideal. And if you mod out by the ideal, you get the Boolean algebra you mapped onto. But in the ordering of theories, modding out by the ideal is that every ideal is a theory, is S. So modding out by S is just looking at things that are bigger than S. So that's an algebraic argument that you know exactly what the cones are. The countable Boolean algebras. But it turns out you can say considerably more. So the crucial point here, property of theories, is whether there are still witnesses for the incompleteness phenomenon. So if you take any S, any theory S, which you cannot extend by one axiom to get a complete theory, that's the incompleteness. There's something that you can't, no finite extensions. This is kind of the name for this, essentially undecidable, whatever. Hereditarily, I never remember which order the adjectives go in. Hereditarily or essentially. So if S can't be pushed up to a complete theory by one axiom, then the Boolean algebra of the finite extensions of S is atomless, because it says no finite, iterating finite extensions is a finite extension. So that means that the image of the finite extensions of S are an atomless Boolean algebra, and the cone above it is just the theory of the ideals of that algebra. It's just exactly the ideals of that algebra. But what was that? That was what DP was. So the finite extensions of S are isomorphic to the finitely axiomatizable theories, and therefore their ideals are isomorphic. And so that says that any S with this property has the same cone above it as the whole theory. So the way to think about this in terms of reverse mathematics is people always say, what happens if I strengthen the base theory? So this says that if you strengthen the base theory, but you just strengthen it by adding on, you taking a recursively axiomatizable extension, for example, then it's still, by Gödel's theorem, it still has this property that no finite extension is complete. And therefore, strengthening the base theory to any recursively axiomatizable theory doesn't change the structure of reverse mathematics relative to the base theory. They're isomorphic. And what about, so the zoo that we had over RCA naught is not in any way changed by strengthening the base theory, any reasonable base theory. What about weaker base theories? So people now are now working on, leaving out doing RCA naught stat, well, which is RCA naught stat, which is there are a whole array of weaker versions that people are working on. And what happens if you go to weaker versions? Well, as long as the Gödel's theorems, the incompleteness phenomena, still apply, then nothing changes. the structure above a weak base theory is again isomorphic to the structure of what we're RCing on. So I want to close with a couple of questions. So I'm hoping that these do not have trivial answers. I guess the last talk, so well, a graduate student didn't propose a new theorem, but he gave a new proof of one of my theorems, different proof, and other people in the audience, like Dana Scott pointed out that I had missed some well-known theorem. So this may happen anytime I talk about this, but the one I think is least likely to have immediate answers is the first one. You may have noticed that I talked a lot about the finitely axiomatizable theories and all the theories, but not very much about the recursively axiomatizable theories. And why is that? It's because I have no idea how to build automorphisms of that structure. The problem is, well, you somehow have to build an automorphism of the finite formulas, which preserves recursive enumerability. Well, the back and forth argument asks questions that are not effective about which things are provable from which others and which aren't. And that's not an effective procedure. So it's hard to see how you're going to build automorphisms and make them be an automorphism of the axiomatizable theories. You now know as much as I know about it, except for the fact that it sounds too much like the lattice of the RE sets, which constructions are very complicated. And whether any of them are relevant here, I don't know. Seems different. So that's the first set of questions, like say something interesting about the axiomatizable theorems. The next question was, though I had been working on it already, it was raised at Ed Slayman about, what about orbits? I mentioned the fact that you take any finite axiomatizable, finite, or any two complete theories, you can have an automorphism which moves one to the other. So that says they form orbits. This is a technical word. You can start with one degree, apply the automorphisms, and see what you get. So those two definable sets are orbits. Are there other orbits? Are there other definable orbits? So I've been thinking about this a bit. That's a week or two. And so the most promising example seems to me to be look at the finite Boolean algebras. Suppose the cone above, you have some finite Boolean algebra, and you have two cones, 2 degrees S and T, and the cone above them is isomorphic to this finite Boolean algebra. Then you might want to know if there's an automorphism taking one to the other. I hadn't made too much progress, and maybe I haven't yet, but this morning I had an idea. But of course, we're getting around one problem I had before, but I haven't yet figured out if it doesn't interfere with the rest of the construction, or if it really works. And it was only for the 4 element Boolean algebra anyway. So that'll be a long way up. There should be some algebraic, some general method of dealing with this. And maybe there is, I just haven't been able to search the literature on Boolean algebras is very large. I'm not familiar with it. So I think that's an interesting question. For arbitrary Boolean algebras, that's a more interesting question, but seems even less likely. We do know someone knows what all the countable Boolean algebras are. As Kettinen has a long, difficult paper characterizing exactly all the countable Boolean algebras in terms of certain invariants. Whether those invariants are enough to guarantee that you can build an automorphism of this structure, not a clue. But here's another way of looking at the question that makes it sound like a well-known algebraic property. That is, seems like the question. I think maybe it is the question, the one for finite Boolean algebras. If you have given a finite sequence of distinct theories and another finite sequence of distinct theories, is there an automorphism that takes the first sequence to the second sequence? So we know it's true if the sequence is length 1, but doing it for finite sequences, I think, should be the same as doing it for the isomorphism for the finite Boolean algebra in the other question. And that, I think that's true, but I haven't checked it since I can't use it. But that makes it look like, what's the, I don't know what this is called, the automorphism thing is an n-pi transit. There's some word for being able to move things, simultaneous sequences of things instead of just one element. So that would be another way of phrasing the question, I think. Okay. So I'm out of time and slides. I just want to thank you all.